So we're going to talk about some of the example homeworks from your section 4.1 homework. And so I've got some sample problems here. I just realized I had to start over because I clicked on the wrong one too quickly. I'll talk to you about that in a minute. But first of all, what is an inverse and why are we talking about that for the beginning of this chapter? I like to address that, and I'm sure you've watched the video lecture already and talk about that as well, but I like to reiterate it here, is that this chapter is about exponential functions and logarithmic functions, and they are related in that they are inverses of one another. So that's same idea as if you think about multiply and divide. Multiply and divide are related to one another, but they're inverses of one another. For example, if we say 2 times 3 is 6, we know 6 divided by 3 is 2. So we're using exactly the same numbers involved in those calculations, but different or in a reverse ordering. And that's sort of the same thing that it is with exponentials and logs. They're going to be related in just that way. So if you have a frame of reference of what exponential work looks like, log is just another way of expressing an exponential in a different ordering, a reverse ordering. Okay, so to start out, we talk about what makes something one-to-one, and that's an important concept at the beginning section because your original function must be one-to-one before it can have an inverse. So logs and exponents meet that requirement. I'll just go ahead and tell you that, so that's how we're able to proceed. But not everything has an inverse function. As we're going to see, if it's not one-to-one, it will not have an inverse. So what makes something one-to-one? So a one-to-one function means that your x values and your y values neither have a repeating value. So I know these don't look like x's, but it's an application problem, so we have actual data and then distance in miles to these cities. And so when you look through the list, none of the city names are repeated. And then the first time I started the video, I said, well, nothing's repeated here. And I went ahead and said, yes, it's one-to-one, but I'm really bad not to look at the details. And notice 1084 repeated. So there is a repeat of the data. If you have any repeating values, either on the x side or the y side, then it is not one-to-one, and we could not do an inverse operation on that. All right, next up, number 2. For a function to have an inverse, it must be that one-to-one idea that I just mentioned. Must be one-to-one. Nothing can be repeated. That's what one-to-one means. All right, so another concept of one-to-one is when we find this inverse function, we make that notation f, like with a -1 exponent, that's the inverse notation. So the domain of this would be the original function f of x, is equal to the range of the inverse. And the range of the original function will be the domain. In other words, whenever you do the inverse function, they switch places. The x and y, as we're going to see in just a little bit, and you probably know from the video lecture earlier, that whenever you do an inverse function, everything about the x and the y switch places. They switch places with each other. So if you're switching x and y is directly related to the domain and range, so it makes sense that domain and range also switch places between the original function and its inverse. Okay, number 4. If function f has an inverse, then the graph of the inverse function can be obtained by reflecting the graph across the line with the equation y equals x. Okay, so that's going to be a rule. We're going to see that whenever we look at it graphically. Whenever you switch the x and y around, it flips the graph over this line. Remember, y equals x is the diagonal line that goes through the origin. Remember, y equals x looks like the spinner on a board game. So this is the line y equals x. So wherever the original equation f is, it flips over that line or reflects over that line. So that's what that question was about. And this one, number 5, refers to the x and y switching places. This is f of x notation. So this is f of x equals y. You can think of that as. That's the x value in a function, and that's its y output if it's a regular function f. So if we're doing the inverse function of that, and it was one-to-one, it met that requirement, the inverse function, then 6 is going to take this place and -3 the other place. So the x and y switch places when you do that inverse. And that's what happens on the graph, it looks like as well. All right, next question, we're going to look at a graph. It says, decide whether the function graph is one-to-one. And so we can use the vertical and the horizontal line test. We're just asking, is anything repeated vertically? We did that back in chapter 2. For regular functions, you can't repeat vertically. Well, one-to-one, you can't repeat horizontally either. So whenever you draw these lines, you never touch the actual graph. You know, this line here that they're asking us about, the graph of the line, it never repeats. It never turns around and has a repeated value anywhere. And whenever we see a line, a linear equation, they're just always like that. You know, lines don't turn around. They're just the same consistent slope all the time. So they're always one-to-one and have an inverse. We're going to see that's true in number 7 as well. So anyway, the answer to that is yes, it's one-to-one. There is no repeating values, no turning around and using a value twice. Number 7, you can really build off that and say, I know this y equals 8x minus 1. That's a linear equation. I know that equation graphs to make a line. So if you know what I said just before, same answer. We know lines are safe. Lines are, I call them friendly lines, you know, because I'm good about those. They're one-to-one. They're regular functions. They're special function. Their domain is negative infinity, positive infinity. So is their range. You only have to graph 2 points and connect the dots. If you know it's a line, you can graph it by y equals mx plus b. It's just our friendliest equation with the most liberty to work within it. Okay, number 8. Is this one-to-one? We might have to think a little harder on number 8. You might have to think a little harder to remember what that graph looks like. But the cubic graph, it twist around the graph like that, remember? And this would be multiplier, makes it a little skinnier graph, or it stretches it vertically. That won't change our values here. And then it moves it down 10 places. That's a vertical shift. So the vertical line test, it is a regular function. And really I know that already because it says f of x. So it's already passed the vertical line test if they're using that notation, you might recall. So I really just need to know, does it repeat this way? Can I hit the picture of that graph more than once horizontally? And so everything is unique there. If you were to make a t-table of values and plug in stuff for x and outputs for y, you would never get a repeated x nor a repeated y. This looks like it almost goes straight up and down, but it's really edging outward. It's going to the right as it goes up. It's not a straight vertical line, so there is no repeats on this graph. So yes, because each x value corresponds to only one y value, and each y value corresponds to only x values. So there's nothing repeating, in a short way of saying it. All right, number 9. Do we know this graph? This time we haven't. It's kind of good to review these. This is our shifting rules for a parabola. The embedded graph is that x squared graph. We know x squared is our parabola graph. This is a horizontal shift of back 1 place. You remember horizontal shifts do the opposite, so -1. And that vertical shift moves it down 5. So it's a parabola right there. The 4 is the multiplier, makes it a little skinnier graph or stretches it vertically. So it looks something like that. It is a regular function. We could f of x notation. They chose not to, but the vertical line does work, vertical line test. But it's not going to pass that horizontal line test. You can see it hits the parabola in 2 places. Anytime I draw a horizontal line, I'm going to graph in 2 places. Except for there, I can hit it once, and of course there I don't hit it at all. But there, you can draw a horizontal line that does hit the graph more than once. So that's a big no. So parabolas are not one-to-one and will not have an inverse equation. Will not have the inverse. Okay, let's see what's next. Number 10. None of those. Yeah. Okay. Number 10, it says, looking at this picture, can you determine if it looks like they're inverses of one another? So remember, the inverse should fold along this line y equals x. If I fold my paper on that line, which I know it's kind of hard to see that, wouldn't need clear paper, but do you think that this graph lies on top of that graph whenever I fold it that way? Gosh, no, it's not working at all there. So whenever this folds over, these lines would sort of go over here, and this would go up there somewhere. They absolutely would not fold onto one another. They're not inverses of one another. Another way to tell is pick a point. Say I pick this point. It looks like the point 1, 0. So on the inverse function, it should have the reverse of that, 0, 1. right there, right? And it does not. This graph is not going through that. So another way to check it, if the visual is kind of foggy to you, pick some points along this curve, x, y points, and ask yourself, if I reverse those, 0, 1, is that on the other graph? Does it go through that point? And it does not. So if either looking at it or analyzing some points, it is not going to have the inverse. Number 11, first of all, do we think this will have an inverse? It's a function, y equals f of x. Oh, sorry, you can't see that. Y equals 4x minus 7. That's a linear equation, right? And we talked about how they're the friendly lines. So they have inverses. They're 1 to 1. So for the function, determine whether it's 1 to 1. So yes, that's a big yes for that. And then find its, if so, then find its inverse function. All right, so here's the first one. We actually did do some real work here. So right now the equation is y equals 4x minus 7. So like I mentioned earlier, inverses, if it's 1 to 1, you replace the x in the y variable to the opposite, x equals 4y minus 7, and then you rearrange it for the new y variable. So I'm going to take the 7 across the line, just rearranging it, getting y alone. Then divide by 4, and y equals x plus 7 over 4. And you could write it that, along with that, it's kind of written in the wrong order, I would say. Y equals, you have to read it backwards. So normally we write it, turn it around and say f inverse, instead of calling this y, this is now the inverse function, is x plus 7 over 4. And another way of saying that would be the, in slope-intercept way, would be 1/4 in front of the x, you know there's a 1 in front of that x, plus 7/4. So that's how we would graph the inverse function, because that's B part. If you can't just kind of look at it and figure it out, and you may need to use your computer little magnifying glass to blow these up. It's kind of hard for me to see that, but try to figure out which one of these. The original function should be, where was that? 4x minus 7. It looks like either one of those they may be exactly the same graph. The original function f should be moved down 4 places and have a slope of 4 over 1. So both of these looks like that could be correct. Now for the inverse function, the dotted line should be 1/4 x plus 7/4. 7/4 is almost exactly 8/4 or 2. Let's kind of estimate that to 2. So the graph should go up 2 places, positive 2, right? That one does. This one goes through, it looks like negative. So it looks like this isn't going to work over here. I think I can go ahead and rule this one out and go with A, that that this starts at 2 and then has a rise of 1, run of 4. Looks like that could be the line. So I'm going to go with A. And you can use, like I said, magnifying, probably see that better. Then it asks me about the domain and range. The domain and range of the original function, right? Regular f, that's the original 4x minus 7. Well, those were lines, that friendly line, so negative infinity has been domain and range. Now then it asks me on the last part of this question to find domain and range of the inverse. So the inverse, I'll switch those, right? If you know the domain and range of the original function, then its inverse should just reverse those. Well, there's nothing really exciting going on here because it's infinity, infinity. So when you reverse those, I'm going to think in my head, I'm putting that one here and this one there, but you cannot tell anything in there because they're exactly the same. All right, so kind of exciting. Number 12, ask you to find f inverse at -3. Now we've done this we've done function work back in chapter 2. We did we would say find f of 3 or f of -3. So normally with a regular function it's f of x, and we would go to x equals that. But since it's the inverse function, it's backwards, so that's the y value. So this means the y value is -3. What is the x value? So go to y equals -3 on your graph. Where's y equals -3? 1, 2, 3. I'm going to say it's right there. And then name the x value. The x value at -3, it looks like, is 0. Do you see this? If I go down -3, the graph just happens to be going through the axis at that point. So the x value at y is -3 is 0. So that's what they're looking for there. And then lastly, watch the video. It says, but we can talk through this one. Decide if it's one-to-one. That's the line again. I stayed with the friendly lines mainly on this for you. So in your lecture, we talked about some other types of graphs and some more complicated versions. But if it's a linear equation, how do I know it's linear? X is to the first, y is to the first. This is y equals mx plus b form. I could graph that line. Lines are friendly. Lines are always one-to-one. All right, I hope that helps. Let me know if you have questions.